Welcome to lecture 46, which is on digital image transformation methods. So before we do the classification of the data, many times we have to transform the data into some other data product so that we can get the better details, and we can also remove the biasness which is present in the data set. So here you will learn that how we can create the new data sets and we can use that data sets in our classification work. So let's begin the lecture. So as we know that the vegetation cover mapping from the satellite image is very important, and vegetation cover is controlling the entire environment of the globe. So this identification of the vegetation cover very accurately is important. Then this can be related, once we identify the vegetation cover, then this can be related to the crop productivity. We can find out the productivity from that vegetation, what is the yield, and also we can develop the models for forecasting. So there are many things we can actually carry out from the data in case we have identified the vegetation cover very accurately. Global surface modeling, land surface temperature, hydrological modeling, ecosystem, all these are requiring the information about the accurate vegetation cover in a catchment or in a particular area. So with that background in the mind, these transformations are designs, and they are very useful transformations in order to clearly identify the vegetation cover, classify the vegetation cover, and separate them out, this vegetation cover, from the other features. So if we look at the different kinds of a transformation, and here we are talking of the spectral transformation only. So a spectral enhancement we are doing with the help of the spectral ratios and the indices. So there are several indices which have been developed on the basis of the wavelength bands, spectral bands. Then we will discuss here the principal component analysis, PCA popularly known as, and the third one is the Tasseled Cap Transformation, TCT. So although there are very large number of transformations which are available nowadays in remote sensing literature, but these are the important one and these are the most popular one which we will discuss in the lecture. Vegetation index, basically we use the two spectral bands data, and we use the spectral properties of these two bands. Let us say one band is in the near infrared band, another is in the red band. So we will use the take the advantages of the two bands, the spectral reflectance in this wavelength region. If you remember the spectral reflectance curve, spectral signature curve, so we are again taking help of that, and we are deriving certain vegetation indices, very useful for identification of different kinds of vegetation which is present. So very useful and very important here could be the difference index. So as you say, the difference index is the difference between the red and near infrared band. So if we have in a certain satellite sensor, if we have the near infrared band data available and we have the infrared or red band available, if we take the difference of the two bands and create a new image, that image is considered to be better for vegetation discrimination. So this kind of indices will give me what is the amount of vegetation. So I can find out the percentage cover of the vegetation, the leaf area index, biomasses, etc. etc. So there are certain important parameters now which could be extracted apart from the mapping the vegetation cover, identifying the types of vegetation cover, leaf area index, biomass, the percentage cover which is present. It will also help me in separating out the vegetation cover from the soil. So sometimes it's difficult if I take the raw data and try to classify the two categories, the soil and the vegetation. right? And the third category is water, if you remember the spectral reflectance curve of these three important classes. So we want to separate them together with the help of these popular indices. We carry out then mapping of the vegetation cover, accurate mapping of the vegetation cover after creating those indices and using them for further analysis. Now, there is a popular indices, vegetation indices, which is called ratio vegetation indices. So, it is called ratio vegetation indices or simple ratio. So, SR or RVI, ratio vegetation, these are the short form of this. Now, when I am calculating these indices, this is the ratio of the two band as the clear from the name. Now, here I am dividing. So, in earlier case I was taking the difference of the two bands. Now, I am dividing. So, as I told you earlier also that the image is like matrix. Mathematically you can represent an image in the form of the DN values with their x and y coordinate systems, row and columns. So, we are dealing with the matrix. So, here in a way mathematically we are dividing one matrix, bigger matrix, by the other bigger matrix of the same size. So, if I have a near infrared band image and I have the red band image, so we are dividing the two pixel by pixel. So, pixel by pixel divisions when we are doing for the entire image, so this is like a global phenomena which we are doing. So, globally we are applying to the whole image the same function. So, this output will indicate the amount of vegetation. The higher values will be associated with the green vegetation cover, the lower values will be indicating me the vegetation cover is not that dense, and it is towards the soil category. Then low values will be soil, ice, water. So, low values of this ratio vegetation index will represent these particular features, and this is the important thing, that it will reduce the effect of atmosphere and the topography. So, when you have learned the topic on atmospheric correction also, there also we have discussed the use of ratio images. So, these are very useful, particularly in hilly areas, particularly where the taller objects are casting a shadow on the ground, there is effect of the topography on the feature. So, if we take the example of ratio images, vegetation indices images of, let us say, thematic mapper data, Landsat thematic mapper data. So, here near infrared divided by red would be, if I take band 4 image and I divide by band 3, I will get the good ratio image as well. If I take the spot satellite data, then B3 divided by B2. So, B3 band is close to the near infrared band and B2 band is close to the red band. If I take the NOAA AVHRR data, then B2 divided by B1. So, different bands are there depending upon the nomenclature of that band, but the generalized form is near infrared band divided by the red band. Now, what the authors in several studies they have done is, we have normally 3 or 4 band data is the common data which is available from the multispectral sensors. We have data available in more than 4 bands also. So, we can create various vegetation indices by the combination of the different bands. So, once we create various vegetation indices, then we can generate a color composite. Like we generate a color composite from the 3 normal bands, we can generate a color composite from the ratio images also. So, if I create 3 ratio images for a particular area and now generate a color composite, superimpose them together after passing through 3 channels. So, sometimes we find that the identification of the features or that image, that color composite will highlight a certain feature much more clearly. So, as I told you that the ratio image will reduce the impact of the terrain, topography or the sun elevation, which we can see simply here. This is the sun direction, and a particular part A is the part which is sunlit part, but a part B is the part which is in the shadow part. So if I take the same part of the hillock, one is in the shadow, B part is in the shadow, A part is the sunlit part, and from the same satellite image, if I take near infrared values, which is 160 DN value, if I take the visible red band, then the 60 is the value. So take the ratio of the two. So if I take the ratio 160 divided by 60, I will get the results 2.666. Now let us take the pixel B, which is in the shadow. So since this is a dark pixel, so in near infrared band I will get the lower value 75. In visible range I will get the lower value, which is 28 as compared to the pixels A. Now if I divide them together, now again I will get 2.678. So after dividing, my output image will have a similar value. One is 2.66 for pixel A and 2.678 for pixel B. So we have the similar values in the output image. So that means the effect of the shadow, effect of the topography has been eliminated from the output data. So such images have been found to be very useful if they belong to the mountainous regions. Now very popular index is normalized difference vegetation index, and there are very large number of studies worldwide carried out where this NDVI has been used very frequently whenever we are dealing with some kind of a land use and land cover mapping, and particularly if we are interested in different kind of vegetation cover, if we are interested in the density of vegetation cover, if we are interested in the agriculture crop mapping, if we are interested in the forest cover mapping. So this is a very useful index which has been used worldwide. And now what it is doing, it is normalizing actually. So if we see the relationship, the NDVI, which is the short form of normalized difference vegetation index, it is the difference of the two band, near infrared minus red band on the top, and divided by the sum of the two bands. So divided by the near infrared plus red band. So what is done is here that we take the difference of the two images and we add the two images together, and the results of that we are dividing it, we are normalizing it, and also we are multiplying the entire thing or adding up by a certain value, so that the values are normalized, they are within 0 to 255 range, and they are all positive value. So we have to take care that the output is not negative. So normally we are dividing it, we are adding by plus 0.5 and in some cases plus 1, so that all the values are positive. As I told you that this is the most widely used index, and it is a good index, but will not eliminate the atmospheric effects as I showed you in the case of the ratio image. So if the image has a lot of topographic shadows variations, then the ratio is better, but for vegetation discrimination, NDVI has been very popularly used by different authors. So the generation of the NDVI, many of the image processing packages now have the inbuilt capabilities to generate those NDVI images. You have to only define the input data sets. If we take the NDVI values of thematic mapper data, then we are taking band 4 and band 3. If we are taking the spot data, then this is band 3 and band 2 data, and if we are taking the NOVA data, it is band 2 and band 1. Now you will see here that it has been multiplied and added with some value. This is the normalization, so that you are getting within a certain range. So in 8-bit data, we know that the output should be between 0 to 255. So a proper care has been taken in that respect. Now I will show you the results of the ratio vegetation indices. So different bands have been used actually to divide one band with the other to create the ratio images. So on the top it is DN2 divided by DN1. The second image is DN3 divided by DN2. So you can see here that these results or black and white images may look like similar, to you, but spectrally they are different. When you like to see the pixel by pixel, their reflectance characteristics, now they are different. So similarly, the different images have been created by dividing one band with the other band. So if I have, for example, in the second row, I have three ratio images which have been created by the division of three different band combinations. So I can now create a color composite, a false color composite from these three images, as we do in the standard practice. So NDVI values, they are sensitive to vigorosity of the vegetation cover and the amount of vegetation cover, the greenness of the vegetation cover, uh, the density of the vegetation cover. So it tells you that how lush green is the vegetation cover. So NDVI values, what will be the range? Range of the NDVI values will lie between -1 to +1. Normally the range of the ratio images will lie between 0 to 4 somewhere. So here the value is between -1 to +1. So that the negative values, because we cannot display the negative value, so we are adding +1 so that the value becomes 0 to 2. Now the value becomes 0 to 2, again we are multiplying by a constant so that the values are stretched together. So this is how we are actually getting, but once we have the values between -1 and +1, then we can do some kind of a correlation, that the negative values will indicate actually the water, the snow cover, the clouds, whereas the higher values will indicate the dense vegetation cover. So this is the kind of a nomenclature which we are using to identify the vegetation, soil cover and the vegetation pixel. So we find that the bare soil reflectance will give us the values which are closer to the 0, somewhere in the middle, and the vegetation will have the positive values 0.1 to 0.7, somewhere that we will get the positive values for the dense vegetation cover. So once we have the NDVI values, and if we carry out some kind of a partition of the values, or what we call as the segmentation of the values, then you can identify the different features, and then this could be used as a training samples. Now you can interactively select some kind of a training samples in order to train your algorithm when you are doing the classification of the image. So this example shows the NDVI image of the whole world. So this is NDVI image which we have obtained from the data, which is a coarser resolution data which covers the entire area, like AVHSR image. It is because here the resolution is coarser but the area covered is much larger. So this gives me a fairly good idea, a comparison where the vegetation cover is good, in which part of the world the vegetation cover is good, and green is showing that, and which part of the country where, which is the arid or the semi-arid part, where vegetation cover is less. So if we have to do something like a climatic modeling kind of a study, then these kind of images are found to be very useful at the global level. Now a comparison between the two now here is ratio vegetation indices shown on the left, where those are the agricultural fields. You can see the boundary, very smooth boundary of the agricultural fields, and NDVI images of the same area. So NDVI images are giving me more clarity as compared to the ratio vegetation indices. So one can now find out with those gray shades differences also, the probably the crops are there, but there are different types of crops which are giving me a different tonal variation in the data. So as far as the further classification is concerned, with the help of some ground truth data, I can do the classification. Now lot of studies are available where we can find out the seasonal changes in the NDVI values, and the seasonal changes could be correlated with the temperature, let us say example. So these are the four images. One is the March 1999, then late May 99 image, July 99 and October 99 image. So NDVI images have been created from these 4 images of different seasons in 1999, and when you try to compare, you can see visually also that you have a very good, in May 99 you have very good dark green areas present, but those green areas have gone and they appearing in July also on the top side, and again these green areas are decreasing, but the March has the maximum kind of a yellow kind of a color, which is indicating the vegetation cover is quite low in the month of March in this season. So one can, from this kind of a change analysis, one can correlate this change with the drought condition, one can correlate the change with the uh, temperature difference in the area. Now you can also use these images for uh, for identifying the healthy vegetation and the distressed vegetation which is the what we call it the damaged vegetation due to some kind of a insect or some other thing. So when we identify that one is the healthy vegetation and another is the stressed vegetation, we can probably link these to the productivity. We can find out the crop yield, and also we can take proper measures. If the vegetation is stressed, the crop is stressed, then probably some measures are required, some pesticides or some other uh, measures are required in order to actually further spread the stressed vegetation. And you can see NDVI, when we are taking the NDVI image of the healthy vegetation cover, taking the 2 band near infrared and the red band, the ratio comes out to be 0.72, and as I told you, higher is the value, better is the vegetation cover. But when we take the NDVI values in the same band data and near infrared and red band data, the ratio comes out to be 0.14. So this is the quite low value, 0.14 is the quite low value. So once we have this kind of a change, we can correlate this with the healthy vegetation and the vegetation which is a kind of a damaged vegetation due to stress or due to some other parameters, and probably can focus in those areas and take proper precautionary measures. Now this has been, as I told you, is related to the vegetation health, and there are many studies where the farmers have been given advice on the basis of the NDVI values which is obtained during the various growing season of the crops. So we get very low values, and this is the example where one image is shown, and you can get totally a different tone as far as the healthy vegetation is concerned, and you can get a totally different tone of the image once you are getting the stress data. But numerically also you can identify and you can find out the range, what is the range and what are those fields in the ground where vegetation cover is stressed. Now this has been related to leaf area index also. So in the leaf area index basically is the total one-sided green leaf area per unit ground surface area. How much is the leaf area as compared to the unit ground surface area. So that is the leaf area index, and very useful to carry out the biomass kind of a study, and this NDVI has been found to be very useful to correlate that. As you can see in the diagram also, that leaf area index has been plotted on the x-axis and NDVI value is plotted on the y-axis. So higher the NDVI value and higher will be the leaf area index, and this is basically responsible for carbon absorption and exchange with the atmosphere. So that is why determination of the leaf area index is also very important. Now there are many large number of vegetation indices which have been proposed in the literature, and depending upon the application and depending upon the identification of a particular feature, various authors have carried out or propose different vegetation indices using the 2 bands data. So if you have the 2 band data with you, then you can try to. Some of these indices will also discriminate the different characteristics of the soil, moist soil, dry soil, etc. can be identified. Now we will discuss the transformations which require more than 2 bands. So far you were using only 2 bands, but you can do the transformations which require maybe the 4 band data. And there are transformations like principal component analysis, which is called popularly PCA, or the Tasseled Cap Transformation, which is called KT transformation. Koth and Thomas were the developer of this, or perpendicular vegetation indices, PVI. There are several this kind of vegetation indices which have been developed, transformations which have been developed, and they require more than 2 bands of the data. So there is a different way actually to slightly carry out the analysis from that. We will find out first of all the correlation between the 2 bands, and we will take those bands which are uncorrelated, or we will make them uncorrelated. So I will discuss here principal component analysis and Tasseled Cap transformation only. So when we have multi-band images, when we have data from the several bands, let us take the thematic mapper data or hyperspectral data. So we have similar kind of images in the different bands. So it will look us similar. So sometimes it is conveying me the similar information. So there is no advantage of the spectral characteristics of the bands. When sometimes we find that they are highly correlated. So if I take band 3 and band 4, it is highly correlated, or band 4 and band 5. If I draw a scatter plot, I will find a straight line. So correlation is very, very good. So I have to neglect actually some of these bands which are highly correlated, and I have to take the bands in my analysis which are uncorrelated bands. So we have to do the uncorrelation activity. We have to create a new axis of the data sets, distribution of the data sets into the new axis where they become uncorrelated, and that is how we are using the PCA and Tasseled Cap and other indices, because the multi-band images sometimes will convey you the same information. So if we see the left diagram where red band and near infrared has been plotted, we are getting a triangular kind of a distribution. So this is a triangular kind of a distribution which we are getting in the left image. But if we see the right image, if I am plotting blue band versus the green band data, so I am getting almost a straight line. So this straight line is indicating that there is a very good correlation. What is the meaning of that? Meaning of that is whatever information content is presented by a blue band, the same information content is presented by the green band. So I will not get much of the advantage if I am using the two together. So one has to be dropped and another has to be taken into the. So one with the least standard deviation one can draw. So ideally I must get this kind of a triangular distribution, so that I can get at the apex of that is the vegetation cover, and then I can get closer to this is the water pixel, and farther to that is the soil pixel. So soil, water and vegetation pixel, I can get good discrimination of that if I get the triangular distribution. So let me explain you now the principal component analysis part. So in the principal component analysis, we are reducing the redundancy of the data. We are taking all the 4 bands. Let us say the example of MSS, which has been given in the literature also, that 4 bands are there, and if we take these 4 bands and try to uncorrelate the data from these 4 bands and have a different axis. So if I am plotting the data, as I have shown you 2 axes, if I am plotting the data on the 4 axis, then it is difficult to show now. I can show maximum 3, but beyond 3, if I have n dimensional data, then I have some kind of a figure, a different figure which is difficult to visualize also. So if I just plot the data, multi-band data on each axis, and then take the dn values from this data, and then try to take some kind of a transformation equations, and using those dn values I calculate the coefficients of that transformation equation and use that coefficients in order to create the new values. So when I create the new output image, the new output image will be PC1, PC2, PC3, PC4. So if I have 4 input band, my output will be 4 PC1 principal component 1, PC2 principal component 2, PC3, PC4 data, and all these data now are uncorrelated with each other. Earlier the 4 bands, some of the bands were correlated, but this has become uncorrelated. I am getting the maximum information content in PC1, the next maximum will be PC2, and the least will be in PC4. So maybe we can take first 3 bands and carry out the analysis. So here what we are doing is, these are our original bands which are plotted on x-axis and plotted on the y-axis, and you can see when I am plotting these bands, I am getting a correlation, good correlation. I can fit in a straight line. I can find out the coefficient of correlation of this spread of the data. So in order to do the transformation, we are doing scaling, rotation and shifting of the axis. So now I have taken my axis here. So this is my, in a way, x-axis, and this is perpendicular to that is y-axis. And if I consider x and y-axis now, the entire data set is now uncorrelated data set. So these two data sets which I am considering along the new axis is very, very useful to me, orthogonal to each other. And the one along x-axis I will call PC1, the one along y-axis I will call PC2, a perpendicular to that will be PC3, like so on. So if I take PC1, PC2 and PC3, it's very, very useful to me. So you can see in the diagram here that the rotation is shown. So rotation of the axis. So this is my x-axis, this is my axis, and I am rotating my x-axis in such a way by a certain degree so that I get the maximum spread of the data along this axis. So this is the range which I can get now, the range of the data along the new axis. So this is my new axis. Now I can get the range of the minimum and the maximum and fit in the ellipsoid within this data sets also. So that's how we are creating the principal component analysis images, and this is the screenshot of a software here which shows that 4 different layers have been created from the 4 input data. So this is PC1, PC2, PC3 and PC4, 4 images have been concerned. So as far as the information content is concerned, PC1 will have the maximum information content, followed by PC2 and PC3. PC4 sometimes it is not used, it is used for geological and other applications. Now the second transformation in a similar way is the Tasseled Cap Transformations, where we are doing that transformation and getting some new output, and new output we will call brightness, greenness, wetness and known such index. So instead of PC1, PC2, PC3, PC4, we are getting brightness, greenness, wetness and known such index. As it is clear from the name itself that brightness index will give me the characteristics of the soil, brightness from the soil reflectance. Greenness will give me different types of vegetation characteristics. Wetness will come from the moisture content or the water content from the data, and known such index will be the geological information content. So this is the Tasseled Cap transformation. The cap name came then once we have a triangular distribution in the 2-dimensional data, and when we have n-dimensional data, we will have the distribution of the data in the form of the cap. So that is why the name has been derived, the Tasseled Cap Transformation. So similar to the same transformation, rotation and translation and shifting of the axis we are doing, and similar to as we have done in PC1, PC2 and PC3, and we are deriving the 4 new output from the 4 input data. So here in this transformation also you will see that we have one axis now which is called wetness axis, another is the brightness axis, the third is the greenness axis. So we are using the characteristics of these 3 data sets in order to carry out the soil mapping. This is called the plane of soils between wetness and the brightness, and between brightness and the greenness it is called the plane of vegetation cover. So we will have different kind of vegetation cover which is distributed in this plane, and different kind of soils which is distributed in the other plane here. So these coefficients have been mathematically derived, and in some of the books these coefficients are also given. This is for MSS data. Landsat MSS data, these 1, 2, 3 and 4 columns, they are actually giving me the coefficients value and brightness, greenness, yellowness and known such index I will get. So I am multiplying first coefficient by the dn plus we are taking the second coefficient plus dn, like that in 4 band data. So similarly, this is the coefficient values for the thematic mapper data, and we can from 7 bands, there are 7 values, 7 columns, I can create brightness, greenness and wetness indexes. So one can see the results of the Tasseled Cap transformations which have been created, greenness, brightness and wetness index. So we can derive lot of information from this kind of a data. So this is another results of the Tasseled Cap transformation. So if we have several input data, then we can get the output data. Here the 4 data sets we are getting, and these 4 data sets now can be used to carry out the classification as we are doing from the normal data now. So this is a wetness index for one study where coefficients are given, thematic mapper data has been used. So TM1, TM2, TM3, TM4, TM5, TM7, these are the bands which have been used. So which we are using the coefficients data of the bands, we can actually derive something like this wetness index. So this is my original image, the first one is the original image and the last one is the pseudo color composite with the wetness index. The second one is the composite layers with the brightness and greenness and the wetness indexes. So I can when we derive the wetness indexes, I can carry out very easily the soil moisture kind of a study from this kind of a data. So the Tasseled Cap is very widely used as NDVI and it is the excellent vegetation index. Now summary of that is the vegetation indices basically will highlight the amount of vegetation cover. They will differentiate between the vegetation and the soil cover, and ratio vegetation indices will remove the atmospheric and the topographical effect. Now the effect of the soil background from the vegetation is minimized. So we can very accurately carry out the classification of the vegetation types, and these indices can be customized for different applications dealing with the earth surface. So the problem with the multispectral data is that you cannot use them straight away raw data. It has to be transformed because sometimes they are highly correlated to each other and we have to uncorrelate the data sets in order to extract the maximum information content from the multispectral images. So this is all about the indices. Thank you.